So this is a top view of the scanner. On the left side here, we can see the camera, and on the right is the actual light source with the rotating specimen in between. The diffuser is just a white sheet of printer paper taped onto a square frame in order to hold it in place. The black strip on top allows for the light to be focused on the specimen, which provides more contrast in the images. The specimen must be as close to the light source as possible for two reasons. One, it is the minimum distance the specimen needs to be from the camera in order to be in focus. And two, the closer the specimen is to the light source, the better it is lit. At the front of the light box, you can see the camera and apparatus. The apparatus allows the camera to be positioned at the right angle and is made out of PVC piping. The three printed black brackets are used to secure it to the light box. At the back, the circuit and motor are connected to a red switch. The motor is wired with a red board, and the program is on a Teensy Arduino 2.0 and a stepper motor driver. A 9-volt battery is also used to power the motor, but the battery does not run in the circuit until the red switch is flipped on. There is a white cord coming out of the left side of the light box connected to the Teensy Arduino on the red board. This cord must be plugged into a USB port of a computer with power for the motor to run. You'll know it is ready when the orange light on the Arduino turns on. The next step is putting the lid on the CT scanner to ensure that no external light enters the system while the scan is being run. Otherwise, the light may cause error in the scanning process, and the entire procedure needs to be done again and again. Now it's time for the camera setting. Make sure the specimen is entirely in frame and in focus, so the scan is as accurate as possible. We set the camera to the interval timer setting, taking 200 pictures at 1-second intervals. Once the camera is ready, go to the back of the scanner to flip the red switch, allowing the 9-volt battery to power the motor and set it in motion. Once that is done, the scanner is ready. Select Start on the camera display to run the scan. At this pace, the scan will take a little over 3 minutes to be fully complete. This is a top view of the scanner with the lid off, so you can see how the specimen rotates once the motor is in motion. This is how the motor works to rotate the specimen, which aligns with the camera's photo capturing timing. Once the pictures obtained have been formatted according to the instructions, the program is ready to be run. The first display is a black and white movie of all the pictures gathered from the scanner. The white parts in the video represent more dense sections, such as seeds and peels, while the black parts represent less dense sections. Next, a video sonogram of all the images is obtained, allowing for a CT cross-section to be gathered. Again, the white parts represent the more dense sections, such as the peels or seeds, and the black parts represent the less dense sections. Now we can see a video of the CT scan cross-section going from the top down. If you look closely, you can see the seeds of the lemon slice and the peels are displayed in white. The 3D models of the specimen are then obtained, allowing the specimen to be rotated in the X, Y, and Z planes for the best viewing angle. The first 3D scan displays the lighter part of the scan as dark and the denser part of the scan as light. The next two models display the scan so that the lighter parts are omitted and the darker parts are represented in color. This type of 3D model allows the dense parts, such as the seeds and peels, to be easier to view. And this is the third one. That concludes the presentation of the scanner and the output images. Hope you have got a clear idea of how this works. For further details and references used to develop the project, please feel free to contact. Thank you.